Okay, I thought we'd make a little video on waves. Let's kind of go through some basics here at the beginning. There are two types of waves. The two types of waves are either longitudinal or transverse. Turns out there are very few longitudinal waves. Longitudinal waves propagate, that means move, in such a way that they are based on compression. Transverse waves, on the other hand, move vertically. So that's a good way to distinguish. If the object is moving up and down, we say it's transverse. If the object is moving left or right, or based on compression, we say it's longitudinal. Now, when talking about a wave, we have a repeating oscillation. That is an oscillation that has a repeating pattern. One of the things that we're going to be spending a lot of time talking about are springs. So a spring with a hanging mass on it is an excellent example of something that undergoes simple harmonic motion. Simple harmonic motion is defined as an object moving in and out of equilibrium. So if we have a mass and it's hanging from the end of a spring, it moves up and down, therefore it produces a transverse wave. As it produces this wave, and we keep an eye on the particle, time is going on, you start to see how you produce a wave. So you get this regular repeating pattern that can be plotted like that. Or sometimes you start with the object at the bottom, and then it goes all the way to the top, and then all the way back to the bottom, and then all the way to the top, and then all the way back to the bottom. Or sometimes you start at the top, and you go all the way to the bottom, all the way back to the top, all the way to the bottom, and all the way back to the top. And this pattern can go on and on and on and on. There's really no limit to how long a wave can go for. Let's talk about some of the basic properties of a wave. So there are a number of places that you have to be able to label on a wave. So one thing I expect you to know is the trough. The trough is the bottom of a wave. Another important part is called the crest. The crest is the top of the wave. If we take the distance from the x-axis to either the crest or the trough, we call this the amplitude. The amplitude always relates to the intensity of a wave. We can also call crests and troughs antinodes, important for understanding sound waves, and nodes, the place where the wave crosses the x-axis. So that's a little bit about the properties. Now when you try to do the problem set, what you're going to find is I'm going to give you some kind of repeating pattern. Pay close attention to the repeating pattern so you know how to produce the wave. So I might say something like, we have an object, maybe an old water bottle or something like that, that's sitting on top of a water wave. So here's our water wave. Here's a little water bottle. And that water bottle is going to move up and down, therefore making a transverse wave. Let's say this water bottle has a mass of 25 grams. Let's say that the water bottle moves up and down 3 centimeters. So it's going to start by going up 3 centimeters in a time period of 1 second. Then down 3 centimeters in the time period of 1 second. Then up 3 centimeters and down 3 centimeters, and you get the idea. This repeating pattern is why it's wave-like. So we start by producing a wave. Now we're going to start at the trough because we started by going up 3. If we went up 1.5, that means we started at the x-axis or node. We're at the bottom of the wave, the trough, or the antinode. So we're going to go all the way up to the top, then we're going to go all the way back to the bottom, then all the way up to the top, and then all the way back to the bottom, and all the way up to the top, and then all the way back to the bottom. That would be considered 3 periods. Each wave that you produce can be called T, or the period. If I draw in my x-axis, which bisects the wave, and we measure the distance from the x-axis to either the crest or trough, once again that's called the amplitude. In this problem, the amplitude would be equal to 1.5 centimeters. Now there's a problem with that. You can't leave it in centimeters. That's a big no-no. we got to turn it into meters. When we turn it into meters, we get 0.015 meters. Remember, everything should be either in meters, seconds, or kilograms. That's going to be a continuing thing here as we learn this. Once we've determined what the amplitude for the problem is, another thing to kind of determine would be the period. So t, or the period, is the time for one complete wave. Here, the time for one complete wave is 2 seconds. Now, as soon as you have your period, you can also turn that on its end. Yes, 2 seconds is the time for a wave, but how many waves would you have per second? That's another way to view the same thing. That's called its reciprocal, or the frequency. Frequency is the number of oscillations you have per second. See, it took two seconds to have a wave, so our frequency then is going to be less than 1. So the frequency here will be 1/2. 1/2 of a what? Hertz. Those are the units we use for frequency. Seconds is for period, hertz is for frequency, amplitude is always measured in meters. Now there's one more bit of information you should know in a problem like this, in addition to how long and how high and how much mass it has. That's how far apart the waves are. So if we go from crest to crest, that's called the wavelength. Or if we go from trough to trough, that's also called the wavelength. Here in this example, my wavelength, I'm just going to make this up arbitrarily. I'll usually tell you in the problem, like on the problem set, the next approaching wave crest is at this distance. I'm just going to use 10 centimeters. So when I come down here and I label my last wave property, we see that we have a wavelength equal to 0.1 meter. Once again, for the same reason, we've got to kind of take it back to its fundamentals. So we have a good picture of a wave. We've got our properties. We're going to kind of use that. We're going to use some formulas. We're going to go through and we're going to solve for some different things. On the problem set, number of things that you got to solve for. One thing you got to solve for, and I'm just going to write these on the left side and then show you how to do them, is the wave velocity. So if we have wave velocity, so understand that the wave itself is really energy, and the energy can propagate through the media, which in this case is water, and it propagates across the water at a certain speed. We can also have something about how stretchy the medium is. This is called the spring constant. Every object has a spring constant, not just springs, surprisingly. Notice the units, newtons per meter. K is the symbol for spring constant. Another thing I'm going to have you find on the problem set is going to be the speed of Lucy. So we're going to do velocity, not wave, let's do water bottle or bottle velocity. In the x direction. Depends on the wave type whether or not you'll get an object propagating. Remember, this was a transverse wave. This is actually going to be a pretty easy one for us. And then we also have bottle velocity in the y direction, some number of meters per second. So this one is referring to the object and how it moves left or right. This is referring to how the object moves vertically or up and down. Important distinguishing point here. This is a transverse wave. So because it's transverse, that means it moves or propagates up and down. Therefore, the x velocity is going to be 0. We can actually solve for the y velocity. Something to consider also is that it's not consistent. It has acceleration. Its velocity changes. So when we solve for this, this is actually going to be the max y velocity. The max y velocity is going to occur when the object crosses the x-axis. It has to stop in order to change direction and come back down. Then it speeds back up to maximum speed, then stops, changes direction, and goes back up. So you're going to find your maximum velocity always occurring at the x direction, and that's what we're going to solve for. So basically, you have to solve for 3 things because 1 is super easy. Let's talk about wave velocity first. So whenever you want to find the velocity of the energy or the wave, we can simply do frequency times wavelength. Now, if you remember earlier, I had us record these things. Here they are right here. Our frequency was 1/2 And my wavelength that I gave you was 0.1. So if we just multiply those two things together, you end up with what you're looking for, which is the velocity of the wave. So if we take 0.5 and then we multiply it by 0.1, you see you get 0.05 for the wave speed. Now that's in meters per second. So it would make sense that the energy might be traveling at 5 centimeters per second. So that's the first thing that we have to find, wave velocity. Another thing I said we want to find is the object velocity in the y direction. Remember, the object velocity in the x direction is really easy because it's a transverse wave. So I'm going to derive a little formula for you here. We've already talked about kinetic energy. Kinetic energy, we have 1/2 mv squared. Turns out if you want to know the potential energy of a spring, you use the spring constant, 1/2 Ka squared. So if we want to be able to solve for this, we're first going to have to be able to find this, which is K. Now, in the lab that you're doing, you can solve for K based on how much the spring stretches. You won't be able to stretch a spring like this. It's just not going to work. It's water. So you put an object on it, it doesn't really pull back. So we have to use the time it takes to be able to do this. So this is the relationship you'll find on your formula sheet. Now, unfortunately, this isn't set up properly. We've got some things not really in the right place. So it's time to do some algebra. So we're going to square the period. We're going to square 2 pi. Watch out here. You've got to keep 2 pi in parentheses. If you don't, you might end up with the wrong number. Okay? So now I have K. K is kind of hanging out down here on the bottom. And what I want to do is I want to move K up to the other side. So if I multiply both sides by K, I move it up. Then I can divide both sides by T squared. And I'm left with K equals 2 pi squared times m over T squared. So that's going to be what we're going to want to use when we do this. I'm going to go ahead and box that up. That's a good formula for us to use. Now that, in combination with our wave properties, are going to help us. It's going to help me to go ahead and solve here. So let's plug our numbers in. 2 pi squared, just from memory, I know that's 39.5. Mass of the water bug at the very beginning of the problem was 25 grams. Now remember, you can't leave it in grams. Got to convert it. 25 grams. Move that decimal place over 3. 0.025 kilograms. Then we're going to divide this by the period squared. Now the time for one wave was 2 seconds, so we make that a 2 and we square it. So all you got to do to find the spring constant is plug into your calculator now. So I'm going to clear out what we had. I'm going to put in 2 pi quantity squared. Here I'll just prove to you that it is 39.5. About 39.47, close enough. Okay, and then we're going to take 0.025, put that in as well, and then divide by 4, 2 squared. So we end up with 0.25 for my spring constant, newtons over meters. So that's just another answer we had to find, 0.25 newtons over meters. Now I can take that and I can plug that back into our one we were working on before. So I'm going to put in a quarter here, 0.25, and then we have a half. We have the amplitude, and we're going to square it. Now the amplitude in this problem was 0.015. So when I multiply across here, 1/2 times the spring constant, so we have 0.5, that's a half, times 0.25, which was the spring constant, times 0.015, which was the amplitude, I end up with a really small number of joules. This is pretty typical for these things that have small spring constants. So the amount of joules that I have for this problem is really small, 2.81 times 10 to the negative 5th joules. Not very much at all, really. Small object though, right? Keep that in mind. Small object, small spring constant. And we end up with a pretty low result for our velocity. So we can then use that energy and we can go ahead and solve for the velocity. So that's not our answer, but we can use that to help us solve for it. In fact, you might just kind of, when you set these up equal to each other, get rid of a couple things. So watch what I'm going to do here. I'm going to cancel the halves. I'm going to get v by itself. So I'm going to get ka squared divided by m. Still v squared, so I got to square root it. This will tell me the velocity of the object in the y direction. So we're going to put in 0.25, put in the amplitude again. The amplitude in this problem was 0.015. Then I'm going to put in the mass. The mass of the water bug, once again, was only 25 grams, 0.025. And we're going to square root it. So this should tell me how fast in meters per second, at a maximum, it moves vertically. Okay, I'm coming up with a velocity in the y direction of the object of 0.39 meters per second. That's 39 centimeters per second at a max. So that's kind of going to get you started on the problem set. Hopefully that's going to go well for you. It's been a while since I made a video. Camera quality isn't quite where I want it. I'm sure that the volume is not great either. But at least you got something to use. Come check out the recitation on Wednesday at 1 o'clock. I'll be able to give you more help then. Hopefully everything's going well for you. No corona problems. I'll see you on Wednesday.